Hello, does anyone can hear me? Cool. So this is my Twitter handle. Please ping me questions, anything we can talk later. So let's roll. I didn't know how to start this presentation to kickstart it, so I'm gonna kickstart whatever I was kickstarted. So I was born in 1986, and this was what happening in 1986. The Halley Comet. I have a friend called Halley because of that. The Mir, that was the first modular space station ever. And Top Gun was the highest grossing movie at the time. And spoiler, Goose dies. And this is the TIOB index for estimated TIOB index for 1986. This is the first column. So the first column, the first language most used is C. The second one is Ada, and the third one is Lisp. And Lisp now is position 27. So what happened? Why was it so popular, and why it's still kind of popular? Clojure is probably way popular than number 27, but what is the story about functional programming? And I hope I can tell you a little bit more about that. So my name is Paulo. I work at BitCrowd. We're an agency based in Berlin, and we really like functional programming. It helps us deliver more, so I hope you can get as excited as I am about that. So let's start in the 1920s. This is David Hilbert. He was a German mathematician, and he kind of wanted to put every mathematician in the world out of business, as Philip Wadler mentions in his awesome talk, Prepositionless Types. He wanted to build an algorithm that would take any statement and formal logic and would output if that statement was true or false. So that was kind of a bold statement to do in the 1920s. We had no computers, no definition of anything, and he wanted to do that. So he released this paper, and there's actually a series of 23 problems, and that's just one of them. And that problem, the decision problem, it's called the Entscheidungsproblem. It sounds better than German. And he needed something more basic than that. He needed that every true statement in mathematics could be proved true, and every false was actually false. He believed that mankind was destined to know it all, was going to know it all, and was just a matter of time. So that's his tomb here. And you cannot read it, but it's written down there. We will know, we must know. So he firmly believed that mathematics was complete, that we will know everything. Until this man came along. This is another German mathematician called Kurt Gödel. And Gödel kind of killed David Hilbert's vibe. In the 1930s, he released his incompleteness theorem. So what Gödel he proved that every system that was based on mathematics was either incomplete or inconsistent. That was very groundbreaking because mathematics would never be complete. And he did that by assigning numbers to operations and statements. It was very smart. It's called Gödel numbering. And encoding statements and operations, he could encode one statement that was very troublesome. He could encode, this statement is not provable. Is this true or false? Who thinks it's true? Who thinks it's false? It's actually undecidable. There is no way to either prove or disprove. So if this is false, then it is provable. But how do you prove something that's false? You cannot, ever. If it is true, it's true, but you can never, ever prove it. So the first one is inconsistency, and the second one is incompleteness. So that was a big debate. is the Entscheidungsproblem decidable? And even more important than that, what is decidable? What is an algorithm? What is the thing that we have to discover? In the 1930s, this man, Alonzo Church, he was working on lambda calculus. And in 1936, if I'm not mistaken, he published a paper that's saying that if computability is defined by everything that you can write in lambda calculus, then yes, the decision problem was indeed undecidable. Gödel came visiting in Stanford, and they kind of didn't like each other. So Gödel said, I don't like your proof, so I'm going to do my own proof of that. You're probably wrong. So he did. So he created general recursive functions in 1936. Also, this man came along. This is Alan Turing. He was one of the brightest minds ever. And he was very interested in computability. And also in 1935 or 36, he also released a paper. This is on computable numbers with an application to the Entscheidungsproblem. And he had a different approach. He created a machine that we now call today the Turing machine. And his approach was, as Alonzo Church saying, if computability is everything that you can write and an infinite tape and making decisions with that tape, then yes, the Entscheidungsproblem is also undecidable. And he kind of solved that using an analogy, very likely for the Entscheidungsproblem. Does anyone know how he solved that? The halting problem. So the halting problem is the equivalent of the Entscheidungsproblem for computability. So 3 papers for the same solution. They're equivalent. There is a strong indication that everything that was there was already there. We just discovered. It was not invented. And there's the Church-Turing equivalency, but that basically says that everything that you can write with a Turing machine, you can write with a general recursive functions or a lambda function. So that big old C program that you have, you can transform it in one lambda function. I kind of think it's like cloning dinosaurs. It's possible, but probably not a good idea. So, cool. We have 3 distinct solutions for one problem. So that is a very strong indication that we're onto something. It's kind of the way that you think of something and you can speak it in 3 different languages, but they all mean the same thing. So we have lambda calculus. Lambda calculus was, as we're going to see it, was a very inspiration for languages like Haskell, Miranda, Elm. General recursive functions was the paper that John McCarthy read to write Lisp. And Turing machines are actually the framework that ended up in C and Fortran. If you like this topic, please watch Philip Wadler's proposition as types. He mentions all that I mentioned and way more to prove that type systems are actually equivalent to propositions in mathematics. And coding is actually the proof of that theorem. It's really interesting, and he's one of the designers of Haskell, so it cannot get better than that. That's the whole definition of lambda calculus. There's nothing more than that, just 3 things. So either a variable definition, function definition, or function application. That's everything that you got. So it's kind of weird because you can see where are integers, where are numbers, booleans. You don't. That's the whole idea of lambda calculus. Everything is a function. Everything can be described as a function. So you have to figure out a way to encode numbers. You have to figure out a way to encode decisions. How do you do that? Functions. So functions, functions, functions. There's no way around it. So Booleans. So if we define Booleans as a function that takes two things, let's define that true just takes the first thing and false can just return the latter. Because Booleans are only made, their function is to make decisions. So if it's true, I'm going to choose the first one, and if it's false, I'm going to choose the latter. So I'm already defined true and false. On that, we can do decision making, if then else. So if we define if then else as a function that takes a Boolean, a true statement and an else statement, then we can just apply that Boolean. So that would be the whole definition of if then else. By the way, this is Haskell code. This compiles and executes. It works, trust me. We have to define operations so we can build logic and mathematics on top of it. So if we start with n is a function that takes two Booleans, which are also functions. And it's defined as you take the first, you apply the first to the latter to the first. And I have to say, the first time that I saw it was really cryptic to me, and it still amazes me. I can understand where it came from, but every time that I see it and think about it, it encodes so much information in such tiny amount of space. So if you use n passing true or false, you apply true to false and true. But true is a function. That true there is a function. And true takes the first parameter. So true, false, and true will just return true. So the latter, and false and true, this will expand to false, true, and false. False will just return the later result, the last one, so you just return false. So you just build n with functions. Or. So or another function, but this time you get the first one, you apply to the first one, and to the latter. Again, you can get, let's not expand too much, but if you apply or to true or false, you get true, true, and false. And true just returns the first one, so you get true. So or true or false is true, and or false, false expands to false, 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 and you just return the later on false, so this returns false. So with those operations, you can build exclusive OR, and you can do an adder, and you can do an ULA, and then you can have a computer with functions, only functions. So that's a really powerful thing to have when you think about those really small units of construction work, and then you go up, and that's where you get your simplicity out of it. But again, we haven't defined numbers. So church, think of that. This is called the church encoding. So how do you define numbers as functions? You can say that 0 is a function that takes a function and an x and apply that function 0 times. Or 1 is a function that takes a function and an x and apply 1 time. And true applies 2 times, 3 apply 3 times, and so on and so on. This is highly theoretical. You have to basically define every integer, but it is possible, and it works. And as this is just an encoding, to get the number back, you have to de-encode it, uncode it. So this is actually Haskell code, and it works. So to get the numero 2 back, you can apply the function 2. The function that you're going to pass is the function +1, and the initial state, the initial value would be 0. So that gives you the number 2 back. Cool. So now we can add numbers. So this is the definition of addition in lambda calculus. So you want to add 2 numbers, but you have to pass a function and an initial value and x. So the way that you do it is you apply n first, and then you apply m first. So you get n times plus m times. And as this is Haskell code, we can define it. So add 1 and 2, we have to pass the function plus 1 and 0. We get 3. Multiplication. A little bit more cryptic, but it makes sense. I kind of think of this because you have m and n as the addition, and you have to apply m times to a function. But what function do you want to pass to m? You want to pass n times f. So for every iteration of m, you're going to pass nf. It's kind of like a for loop. I also think of that. So kind of the n being the inner loop and m being the outer loop. But they're just analogies. This is the complete definition. So we can combine them. So if we multiply 2 and 3 and add 1, we get 7. We just have to pass our plus 1 and 0 functions. And this is the 1940s. Computers were people. They were people following instructions on paper. We had no electronic computers, nothing. We had no compilers and no programming languages. This is highly theoretical, but it worked. You could write functional programs on paper and execute them. You just had to have a lot of patience and a lot of paper. Until this man came along. This is John McCarthy. He was a researcher on AI in Princeton, if I'm not mistaken, and he needed a really powerful language that he could express intelligence with it. So reading Gödel's paper on general recursive functions, he created Lisp. And Lisp is the first implemented functional programming language that you have in the world. So this is how you could write factorial in the 1960s. So you still have lambdas, you have helpers, but the idea is pretty much alike. You just have definitions of functions and function applications. So this is the state of functional programming in the 1960s. And this was really, it's still very, very powerful that we can have in ClojureScript. They're all descendants of that. And that explains the TIOBE index that you have in 1986. So during that time being, during the 1960s to the 1990s, you have lots of programming languages, and Church Basis was there. So everyone could read it, and everyone could define their own functional programming language. Especially if you write on top of lambda calculus, you could get a really good programming language in a really small amount of time. But it's hard myself to put in that way, but it's the 1960s. You don't have internet. You don't have email. You don't have WhatsApp. How do you collaborate on a language with someone in Europe when you have no internet? So what happened was just a really large amount of programming languages. Some were functional, some were not. But collaboration was really hard. How do you collaborate with nothing? So, but the core of those languages was kind of the same because they were based on something that was discovered, not invented. So most researchers were kind of working on the same thing, almost like a waste of time. In the 1990s, this man, Paul Hudak, he passed away in 2015, unfortunately, but he wanted to change that. So what he did is he had an idea to get the core of all those languages and create one that everyone could participate, everyone could collaborate. And he did. So in the 1990s, he invited a couple of people to Princeton, and they defined what would be Haskell. Again, all based on mathematics from the 1930s. It was all there. It was just kind of like RFC. They were heavily inspired by the work of this man. This is Haskell Curry. Actually, Curry was the first name of Haskell, but he was a really he was one of the first people who actually got lambda calculus and expanded. And he is the discoverer, but not inventor, but discoverer of the Y Combinator. Not this. But this is the Y Combinator, because we haven't talking about recursion. How do you define a function in terms of itself? So you cannot do that in lambda calculus without the Y Combinator. And now you kind of know why the Y Combinator calls itself that way, because the Y Combinator is a function that outputs functions. So it's a function that creates other functions. As the Y Combinator, the company is a company that creates other companies. It's a pretty cool name. So there you have it. In the early 1920s, you have Haskell being the first pattern to follow on lambda calculus-based languages. And the thing that you get when you build your function, your programming language on top of functions like that, is by design you get laziness. So there's a lot of buzz today about concurrency and using cores in functional programming, but I truly think it's a consequence way down the line. I think a more powerful consequence is that you can define functions and you can apply them wherever you want or whenever you need. So being able to run in multiple cores, that's just a detail. So that's where your power comes from. So if we're lazy, we can basically have an infinite list. So this is the infinite list of natural numbers. But if we apply the function take and just pass 20, we'll just take the first 20 from the infinite list. That works with functions, because functions. So you can map on infinite list. So if we map the function plus 1 and an infinite list of the natural numbers, we'll get an infinite list. But we can just take the first 20 or 10. So in this case, taking the first 20 numbers of the infinite list, we'll get 2 to 21. So that is a really, really powerful consequence actually, because you can separate the producer from the consumer. You can say, I'm going to produce this infinite list, this infinite stream, and you can consume it wherever, however you want, whenever you want. But my power of expressiveness is there. We can use the iterate function. Clojure implements that. That's really cool. Iterate function takes a function and an initial value and will return you the infinite list of that function application to that value. So x, f of x, f of x, and so on. So if we pass the function times 3 to 1, but only take 5, we'll get 1, 3, 9, 27, and 81. So again, separating producer from the consumer, we can wrap up iterate times 3, 1, and then API, and we can expose that, and we can have multiple consumers doing that. So expressiveness. This is a really important consequence of functional programming. Expressiveness comes by design. So I hope that gave you a little bit of context on how expressiveness, it's a consequence of having functions as first-class parameters, actually the basis of your language. So expressiveness, infinite list of events, define functions to be applied at those events, and the result is an infinite list of side effects. I can apply that to UI. So if I have an infinite list of events, mouse clicks, keyboard, mouse movements, I can define pure functions to be applied, to that infinite stream of events. And the result will also be an infinite stream of events. But it can be controlled, right? It passes from a event-based language to a more time-based. So you don't have to write callbacks, you don't have to connect that event to that callback, you can define a behavior. You can apply that behavior to different types of infinite streams. So that is really powerful on UI. Advantages. So no callbacks. Callback hell is a really big problem for me. I don't like to complain about JavaScript. I really like the community. I think the language is really powerful, but I think callbacks they're not ingrained in my mindset. So every time you have to define a callback, I kind of get lost a little bit. So I prefer that kind of mindset instead of the event-based. And you can define pure functions. And you can apply that function to different contexts and different streams, different infinite streams. And you kind of pass that handling event-based to time-based, which is also cool. But still, you get all the benefits from functional programming. So that is the purpose that Elm was born. So let's get really practical this time. So lift takes a function as a parameter, a signal. You can see signal as an infinite stream of events and returns an infinite stream of events. So you have a function that takes from A to B and a parameter that is an infinite stream of events of type A, and it'll give you the infinite streams of events of type B. So that's a very basic example that Evan, the creator, gives. So if you lift, the function is consonant to the stream of the last press events of your keyboard. So hello is an infinite stream of events that could have more events on that. Event is a little bit a wrong word to use it, but still the analogies hold. So if you lift that function, you get an infinite stream of results, which is true, false, true, true, false. Fold P. As Evan also mentions, this could be read as fold from the past. This is a way that you can carry state on your Elm application. This is not true for Elm. I'm talking about Elm now, but this is a pattern. This is implemented in several functional programming languages, but the way that it works, you have your initial state. And our case here is that little 0 here. So initial state is 0. Your infinite stream is, again, the last press keyboards. And then you have a function that takes your event and the state and gives you another state. So the function here takes the key, the count, and just increments the count. So hello, in this case, would be transported to 1, 2, 3, and 4. So you apply the same idea just to a different scenario. Again, this is really powerful. This is kind of half of truth because there are no more signals in Elm 17. There's a nice blog post called Farewell to Functional Reactive Programming. It's really nice. Please read it. Even if you don't want to try Elm, it's how functional reactive programming could be seen as a subset of a larger group, but it's still the analogies hold. All the analogies hold. So I like making games. Games are, for me, really fun. They are very reactive. They're hard to make. And I wanted to build the Flappy Bird because it's kind of simple in theory, but hard to make. And what did I need to do? So I needed to generate pipes every X seconds. I needed to handle the key press event. I also needed to handle collision. And to be a little different, I wanted to have a live scoreboard. So I thought, I don't know about the live scoreboard, but I'm pretty sure I can handle the first 3 using Elm. So how do I do that? So Elm now has subscriptions, is the replacement of signals. It's a little different, but all the analogies pass, as I said, hold. Now subscriptions, they generate messages, and your application will work as passing messages to one part of the application to another. So this is the actual subscriptions from the game that I did. Batch here is just a function that will take a list of subscriptions and generate one subscription. So I have a subscription that will tell me where the animation change. I have a subscription that will tell me when the user press a key down. I'll have one subscription to ask me for the top layers from the server. I have one to generate pipe, and another one for sockets. We don't have to get into that later, but let's take this example here. So time.every time second will generate an infinite stream of events, every event happening 1 second apart from each other. And what I'm doing here is, as with signals, I'm applying the function as for top players on every little event. The same thing happens to generate pipe. So I'm generating a pipe every 2 seconds now. And on that infinite stream of events, I'm applying the function generate pipe. This is actually an union type. So as for top layers, key down, time update, they're all union types. But if you've been following this talk, you can guess what union types are. They are functions. So that's the idea. Subscription generate messages. User can generate messages as well. So when you click, you can generate a message, but the application itself can generate messages to itself. So you have to have a way to update your state based on messaging. And your state transformation will be concentrated on where you got your messages. So this is called the update function. So this is the simplification of the update function on the game that I did. So you just have to say, am I playing or not? Paused. So if my message is ask for top players, I'm going to ask for the top players. So I have to send my score from time to time. So this is a message that comes not from subscriptions, but from the application itself. I have to handle the message key down, and that message has an inner data, which is the key code that you probably want to check. So generate pipe actually has a parameter, the Unix timestamp, that I don't care. But again, you have a concentrated state transformation place in your code. This is not, again, this is not specific to Elm. So if you take a look at the type definition of the update function, it takes a message, a state, and will output a new state and a message. This is called the state monad. This is really, really powerful. There is a book on Haskell called Learn Yourself Haskell, which explains that all the important monads really in a nice way. So this is a really important monad to have. So Redux kind of gets that idea and implements it in a very nice way. Dan Abramov, am I right? Dan Abramov, the creator of Redux, he mentions that he looked at Elm's architecture to get that state information to be applied in Redux. And now we have a new state. So this function will output a new state, and we have to have the visualization of that state. So we have to have a view function. This is not the actual view function of the game, but as this is not an Elm tutorial, and it shouldn't be, this is just more important to get the type signature. So you have a state as your parameter, and you just output the HTML representation of that state. So I kind of made a game, and it works. And it has a live score that you can play with your friends. And it handles collision. So my idea here is try to learn something new, and if you can, I would say try to build a game. They're really, really fun to make. They will teach you really important things, and they'll show you design patterns that are there for ages. And for me, games are the ultimate reactiveness that you can get on an application, because you have to handle multiple events coming from multiple ways, and you have to combine them. So, summary for me is functional programming. It's not invented as it is discovered. I would highly recommend the book called Learn Yourself Haskell. It will get yourself for every detail of that craziness that I was calling Haskell. So it will show you that it has really important constructs that if you're not going to apply it, is really important to learn. And after reading that book, I kind of asked myself, am I using a programming language that was invented or discovered? And I wanted to use one that was invented and not discovered. And again, expressiveness is by design. It's not something that you can get if you don't think about it first. And yeah, thank you. Oh yeah, let me check if there are questions. But please ping me after, or we can have a beer or coffee. So again, thank you so much.